Okay, so lecture 6, the non-homogeneous case. This is the setting. We have n linear differential equations in n unknowns, and we have g1, g2 up to gn. So, as you can see, let me check something. As you see, I have written this in this format so that X is in fact the Xi's, A is the matrix, and for now I assume that A is it has constant entries, and GT is this, which is a vector of functions here. So this GT is in fact gives me the non-homogeneity of this equation. So that's the non-homogeneous part, and or the forcing function, whatever. And let lambda 1 up to lambda n be eigenvalues of A, and the V1 up to Vn corresponding linearly independent eigenvectors. Then this matrix with eigenvectors as columns is invertible because these are linearly independent, and then D is this diagonal matrix with corresponding eigenvalues. Okay, now let me erase this and continue. So okay, method 1. Using so, well, we know that the matrix A times that V is V times D, and this gives me the inverse A, V is D. Okay, so number 1. So I will go step by step and tell you what to do. Step 1, you let Y be Y1 up to Yn be V inverse X. V inverse, because V inverse exists, so V inverse X, just multiply V inverse by X and you get this. But each one of them, Y1 is like a linear combination of the X's, okay? So, and this gives me that X in fact is a Y. So, number 2, plug in the equation. Okay, what was the equation? The differential equation was X prime was AX plus GT. So if I plug in, that is A Y prime, A Y prime, that's X prime, equals A sorry, this is not A, this is V. So, where did I get this V? Okay, so A, V, Y, plus GT. Okay. Now, if I multiply from the left, if I multiply from left by this is V. Why? I'm just making myself confused. So this is V. So if I multiply from left by V inverse, this is what I get. So V inverse V is I, so this one goes away. So I have V inverse A V Y plus V inverse GT. Okay, now I know that this one is D from here, so this one is D. And this is just another matrix, so this will be some matrix like this of functions h1t up to hnt. So this results in this differential equation, or this system, dy plus some ht. Okay, so let's call this ht. That's another function. Okay, so let's let me erase this and write down step 3. Step 3 is, so I have this y prime is dy plus some ht. So let's expand this thing. If I expand this, I have one y1 prime. This is lambda 1, lambda 2 times y. So the lambdas are in the diagonal, there are diagonal terms. So what do I get? I just get a matrix like y1, y2. So this is in fact y1, lambda 1, lambda 1, y1. Plus h1t, y2 prime, lambda 2, y2, h2t, up to yn prime, lambda n, yn plus hnt. Okay, so each one of them is just a differential equation, a first order differential equation, and they are not connected in any sense. They are not intertangled, so you don't see any y2, any y1 here. So each one of them is separate. They are just on their own. So this one will give me y1. This one will give me y2. And this one will give me yn, okay? So each is a first order differential equation in yj or some j. Okay, so each one is first order. Remember, you should take this, for example, for yj prime minus lambda j. Yj is hjt. And remember that you have e to power blah blah blah. So I just leave it to you. I'm not going to do that. So that is step 3. Step 4. Well, then we have the yi's or yj's. Then x was what? X was ay, right? Sorry, vy. Okay. So that's it. So you have these things. These are like now functions of time. I mean, they were functions of time, but you have some explicit functions. So that is in fact v times what you have found. So, well, you can just put all these steps together. Maybe just in 2 steps or 3 steps. I don't care. But that's what you do. Well, when you do this here, at least maybe geometrically, or maybe you just feel what's happening. And there's a more differential equation than algebra, except for finding eigenvalues and eigenvectors. And you can find it, so you can find a general solution. In fact, in this case, you find general solutions with constants, so that is in fact the complement. You find the general solution with some constants for the complementary part, and because there was no initial condition, so and the other part which doesn't have any constants, that is in fact the part that comes from the forcing function. Okay, so this is one way. To be honest with you, this is just too much for me. I would rather do it in a much simpler way. So let's do something else. Method number 2. Now, Laplace transform, I think it's much simpler, and well, you have access to, say, Wolfram alpha or Mathematica or something, and you immediately can solve it. I'm not saying that the other one is not immediate, but that one needs more work. So the differential equation was this: x prime is ax plus gt. Applying Laplace transform, the a is constant, so that is a Laplace of x plus Laplace of gt. But this one is like x1, x2, x3. So let me write this explicitly. So x1 prime, x2 prime, dot, 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 xn prime. And if I apply Laplace, then it will be, it's applied to each one of them. We are integrating each one from 0 to infinity, blah, blah, you know the integral. So this will be s, x1, s, x2, s, xn, assuming that initial conditions are 0. So assuming that x at 0 is simply 0. So let's assume that it's 0. When we have forcing function, most often we can assume that the system starts from 0. So it doesn't have anything else. So I have, as you can see, that is simply s times s. This is simply s times x1 dot 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 xn, right? So this one will become s Laplace of x, right? That's not x1, sorry, this is in fact Laplace, not a mistake. That is Laplace of x1. Laplace of x2. Right? So that's s Laplace of x, and on this side I just have a Laplace of x plus Laplace of gt. So I have to solve for Lx, Laplace of x. So I bring this one to this side, and this is a matrix A by n by n. This is a constant. Remember, it's like that a minus lambda I. So this will be Si in fact. So when I write this here, S times these things, it's like writing Si times this. Okay? Because I have to subtract A from that Si, so it's the same thing. So I write Si for this one, then minus A times Laplace x, and this equals Laplace of So L x is inverse of this, Si minus A, inverse Laplace of GT. That's it. So you have Laplace of x, and x will be Laplace inverse of this guy inside. Write it as I minus A inverse Laplace of G t. Okay. So the only thing I have to do is finding inverse of a matrix which has a variable S. It's easy when you have 2 by 2, but more than 2 by 2, definitely you can use Mathematica or some program to explicitly find that Si minus A inverse. Another thing you see, that looks like that formula A minus lambda I, determinant of A minus lambda I. Okay, so example. So that's the solution. That is the solution when you use Laplace. And I started here and here, right? So it's just 1, 2, 3, almost 3 lines, not steps. Except, yeah, I know. Well, you might say, gee, that is not easy to find Laplace inverse here. Laplace of x is okay, but the Laplace of this one is okay. But inverse, you're kidding me? But yeah, I know. But anyway, so I have this. This is in fact from the textbook, and I wrote it somewhere here. Example, yeah, the example and the book is this. So I have x1 prime is minus 2x1 plus x2 plus 2e to the power negative t. x2 prime is x1 minus 2x2 plus 3t. So I need from that formula, the only thing I need is the Laplace of these two, right? So I know I should find Laplace inverse of Si minus A inverse times Laplace of this GT. Now GT is this. So let me write it. X prime is minus 2, 1, 1 minus 2, x plus gt is 2e to the power negative t and 3t. Okay? So let's find the Laplace of gt, and the Laplace of 2e to the power negative t and 3t is Laplace of each one separately. So that is in fact 2 over s plus 1 and 3 over s squared. Right? So we also need this, inverse of this. So let's write this down more carefully. So this is SI, so the SI will be S. Remember, this is A, right? This is my A. It's not A minus lambda I. I could have written it like that, then I should have written minus here, but that's okay. So be careful, this is so S minus that, so it's S plus 2, minus 1, minus 1, S plus 2, inverse. Now recall the inverse of 2 by 2 matrix, so if you just know how to find inverse of a 2 by 2 matrix, you're okay, that's all you need. So remember that was the determinant of this, that was a 1 over determinant of this matrix, times, if I remember correctly, that was the A, this one, and this one, the interchange. Well, in this case, there is no interchange, but they're the same. And this one, they lose the negatives because that's minus minus, right? So I have 1 and 1. Okay, so using that formula for inverse of a 2 by 2 matrix, we have this. Determinant is S plus 2 squared. So 1 over S plus 2 squared, minus 1. Minus 1 times this. S plus 2, 1, 1, S plus 2. Okay. So, I have everything ready to find the Laplace inverse of this thing, so let me erase up here, and I need this thing, and I need this, right? So x basically is Laplace inverse of this thing, 1 over, if I square it, or if I just say factorize that, that will be s plus 1 times s plus 3, right? So that is s plus 1 times s plus 3. And that is s plus 2, 1 s plus 2 times this 2 over s plus 1 and 3 over s squared. Right? So this is that s minus 1 inverse. This is this thing, and this is this thing. Okay? So, well, as I said, and I say it again, if you have 2 by 2 matrix, or 2 equations and 2 unknowns, finding the inverse of this is easy. Just use that formula for inverse and you have it. Now, so let me just do the calculations here and write it down for you. So I have to find the Laplace inverse of, well, this one is just the determinant, that's plus 1, that's plus 3. And that will be this one times this one is just 2, plus 3 over s squared. This one times that one is 2s plus 1, plus 2 times s plus 2 over s plus 1. So that's Laplace inverse of, well, I put them together and I have it here after simplifying everything. So this will be 2s squared plus 3 divided by s squared times s plus 1, s plus 3. And the second one will be, you see this is s squared, so on top I have s squared, 2s squared, and plus 3 times s plus 2 squared, you say, was it? That's e to the power. Why do I have e to the power? Minus t. I can remember that was e to the power minus t. So this calculator is square, right? So let me double check here what is going on. I have s plus 1, s plus 1, so that is okay. But why do I have s plus 2 here? Of that s plus 1. So, okay, let's say this, there is something here which is not correct. Oh, this is let's see, that is this one time this one is this one time this one is this, yeah, so okay, so that's mistake. Okay, so that one is 2 times s squared, 2s squared plus 2s plus 1 times this. I wrote down the 2 outside, s plus 2, and the whole thing is divided by s squared times s plus 1 squared times s plus 3. Okay? So this gives me x1, x2 is a Laplace inverse of top one. I'm not going to write it, and Laplace inverse of the bottom one. Now what you can do is, that's what I did. So you can use Wolfram Alpha. I didn't use Mathematica. I wanted to see how Wolfram Alpha works. So you can use Wolfram Alpha, and the command that I use in Mathematica is in fact the command a part. A part means do the partial fraction. So you can just say a part, say this one for example, will be something like this. 2s squared plus 3 divided by, what's the denominator, divided by, and be careful on parentheses here. S squared times s plus 1 times s plus 3. 1 and 2 and 3, there is another parenthesis here. So, and then suppress this. I have the first one, so let me write the first one for you. And I did the first one. So the first one, if you, I think the first one was correct. I made a mistake here. And so the first one will be Laplace inverse. The a part gave me this 1 over s squared plus 5 over 2 s plus 1. And be careful, when you do a part, it will give you 5 over 2 times s plus 1. Don't leave it like that. Write everything, this should be s plus 1, 1s plus something. Okay, so the coefficient of s should be 1. So if you see a number in the denominator or even negatives, write the negatives here. Minus 7 over 6 s plus 3 and minus 4/3 over s. Okay? So the a part gave me this, and so x1 will be let me just write x1. So this is x1. This guy here is x1. So x1 will be 1 over a square, that is key, right? Plus 5 over 2 e to power minus t, minus 7 over 6 e to power minus 2t, minus 4/3. So with 0 initial condition, that is what I get for the answer in this case. Okay, let me see what else we have here. Well, I guess that's all I want you to know from linear systems. And next time I will start the nonlinear systems and how to linearize them and stability of solutions. And I'm not sure, that takes like 2 or 3 maybe lectures or something. Okay, so have fun.